Don't forget to subscribe and ring that bell.
Welcome back to the 2019. We finished free response question 1, and we are now on to free response question numero 2. Okay? This is the last question that we get a graphing calculator for. And this dude here, yes! He's like angry happy. He's like going to eat this problem up, and you know what? So are we. We're going to eat this problem up. Let's get done with it and move on to the short answer questions that we do not get a calculator for. Let's go. Oh, man, I tell you what, I love getting tables. I love tables and graphs that are made up of line segments and half circles or quarter circles. They're just so easy. Number 2 states, the velocity of particle P moving along the x-axis is given by the differentiable function Vp, where Vp of t is measured in meters per hour and t is measured in hours. Selected values of Vp of t are shown in the table above. Particle P is at the origin at time t equals 0. Okay. Justify, this is 2a now, justify why there must be at least one time t for t in between 0.3 and 2.8 inclusive, at which v prime of pt, vp prime of t, whatever, the acceleration of particle p equals 0 meters per hour per hour. Whoo! Mean value theorem, people. Okay? Mean value theorem. The mean value theorem states that instead of using y and x, we'll use this Vp of t. So Vp of t, it's basically change in y over change in x. Okay? If we have an interval, which we do, okay, that the average change in rate between these two intervals, that's what we do our change in y over change in x, has to equal the derivative at one point c in between this interval. It has to, especially if it's differentiable everywhere. We can take the derivative everywhere. So let's figure out what our change in y over change in x is. Okay, so we're going from 0.3 to 0.8. Those are our x values. And here are the y values. Well, I can see right now my change in y from 55 to 55, that's 0. It's going to be 0. So let's do this. Let's do this proper. Okay, so 55 minus 55. This is y2 and y1. Okay, in case you need me to do this is y1, y2, x2, x1. All right? Over 2.8 minus 0.3. That's 0 over, what's that, 2.5? That just equals 0. That has to equal the derivative at some point c in between. So here it is. And justify. I mean, I think by the mean value theorem, but let's just write a little note. Okay, say by the mean value theorem, there is some point c between 0.3 and 2.8 where f prime of c equals 0. And here's our math work for it. I mean, you know, mean value theorem. God, I love it. You should love it too. 2b, use a trapezoidal sum with 3 subintervals from 0 to 0.3, 0.3 to 1.7, and 1.7 to 2.8 to approximate the value of the integral from 0 to 2.8 of Vp of t dt. No label is needed. We just need a number. Okay, let's establish our 3 subintervals, okay? Playful, the first one will go from 0 to 0.3. That width is 0.3. The next subinterval goes from 0.3 to 1.7. The width of this subinterval is 1.4. That's from here to here. Okay, and 0.3, in case you couldn't tell, was from here to here. And last but not least, we'll do, I guess we'll go gray. 1.7 to 2.8. Okay, that width from here to here is 1.1. Now, the way the trapezoidal rule works is as follows. I take every y value in my interval, and the bookends, the first one and the last one, do not get doubled. For example, I take my width and divide it by 2, and then all my y values, starting with my first one, I don't double. But then I multiply the next one by 2. I multiply the next one by 2, dot, dot, dot. But the very last one, I don't double either. I call these the bookends. I do not double the bookends. All the books in between that are being held by the bookends get doubled. In the case of our problem here, okay, I only have 2 bookends. I do not have anything in the middle that's going to be doubled. So I take my width, which is 0.3, divided by 2, and I multiply that times 0 plus 55. Okay, and I add that, and I got to do the trapezoid rule here. Why do I have to do 3 different ones? Because the widths are all different. If they were all the same, then I could do it all in one. So I have my width 1.4 over 2. It's always over 2. And I have a bookend of 55 and negative 29. 55 plus negative 29. I add that to my last trapezoid rule, where my width is 1.1 over 2. Again, I have no bookends. I just go from negative 29 to 55. And I have a calculator. I mean, the only thing that's going to prevent you from getting this problem wrong is mistyping it into the calculator. So let's put this way up here. Let's see if we can get this higher so we get the screen in. Bam, 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 bam. All right, so this is going to start. Okay, turn this on. We can use fractions. Why not? 0.3 over 2. And we're going to add 0 plus 55. Plus, let's make sure we got that right. We did. The next thing is we have another fraction, which happens to be 1.4 over 2. And in that parenthesis is 55 plus a negative 29. Plus another fraction, kids. It's 1.1 over 2. And in that parenthesis, you're multiplying it times negative 29 plus 55. I think I typed it all in great, and we get 40.75. I mean, we don't have to round. They don't ask us for anything in particular in terms of label. I mean, these first 2 sections, A and B, you know what I'm going to say, kids, is cake. All right, 2C looks like it's a little complicated, but let's check it out. 2C states, a second particle, Q, moves along the x-axis so that its velocity for time in between 0 and 4 inclusive is given by the Q of t. 45 times the square root of t, yeah, we'll call that. 45 times the square root of t times cosine of 0.063 t squared meters per hour. Find the time interval in which the velocity of particle Q is at least 60 meters per hour. Then we got to find the distance traveled by particle Q during that interval where the velocity of particle Q is 60, well, at least 60 meters per hour. This is going to be another easy one with the calculator. But let me explain this here. First, we need to find the time. So I need some t values. Well, it's going to be an interval where the velocity of Q is at least 60. Right? They give us velocity. Okay, that'd be nice if I'll just do it this way. They give us velocity. So when is this at least 60? There's going to be an interval. Okay. Once we do that, at that point, we're going to find the distance traveled. If I have velocity and I need the distance traveled, that is just simple integration. So what are the bounds? The interval that we come up with. That's it. And this calculator is going to help us do everything. So the first thing we should do, let's focus on the interval where my velocity for Q is at least 60. What I'm going to do is I'm going to put this in the calculator in Y1, and in Y2 in red, I'll put 60 in the calculator. And I want to see where this is actually above this 60 in the calculator. That's it. So let's put this on. Let's go to y equals. And we got this fancy equation that we're going to type in here. And the fancy equation is 45 times the square root, we're going to use x, times the cosine of 0.063 x squared. All right? And then we want to know when that's over 60. Now, they gave us an interval. Okay, they give us this interval right here. So my axes, I'm just going to go between 0 and 4 on the x-axis, right there. All right? And I know that I want to, at least on the y, go to 60. Okay? So let's go back here. So let's look at my window. Let's go between 0 and 4. And we'll go between 0. And if we need to see the graph of y equals 60, let's go to 100 by 10s. Okay? If we got to change the window, we will. Okay, so this is my velocity. Okay, that's going up. That's all nice. That's fine and dandy, kids. That's nice. Like, okay, it's coming back down. And this is the line y equals 60. Boom once, boom twice. We want to figure out where my velocity, which is this line, is above 60, which is this line, between this point and between this point. And if we got to like justify or show our work, we can just sketch this graph. All right, so the first thing I'm going to do is I am going to sketch this graph. That looks like before 2 and 3.5, somewhere around there. So let's do this, because if this were the test, wow. How about that? There we go. Okay, here's 4. Here's 2, 1, 3, 0. Here's 60. All right, so I'm going to say this is where y equals 60, where y equals 60. And now I got this stinky thing that looks like it crosses around here maybe, and here. It's going to come do this thing where it kind of comes up, goes like this. I want to find these 2 points. So t is approximately, and t is approximately. That's my interval, where my velocity of q is above 60 or equal to 60. All right? So let's, in our calculator, do the intersect function, shall we? Second, trace. Choice 5 is intersect. Well, let's just get, okay, since we have 2, we need to get close to the one we want to do. It looks like we're right on it. As long as we're close to it. I could be right. That's fine. I'm going to do the intersection on the left because my little spider dude is closer to that intersection point. Hit enter 3 times. And if we look at the bottom left of our screen in red, it's 1.866. 1.866. All right? We have to do this one more time. one more time. Oh, it's a new Blink-182 song. It's fantastic. Second trace, and we're going to go to intersect again. But this time, I need to make sure that my spider dude is closer to the other intersection point. If it is not, it will still return this one. If I'm closer to this one, it will return this value. I'm clearly closer to this one, so I hit enter 3 times. 3.519. So that's 3.519. So let's actually answer this. The time interval during which my velocity for Q is at least 60. That means it can equal 60, 60 or bigger. So I am not going to do this. Since it can equal 60, that means I need to have equal signs under there. That's the interval. Now, the next thing that part C is asking us for is the distance traveled. If I have velocity, I integrate velocity. In this case, v q of t dt from the bounds in this interval, 1.866 to 3.519. It doesn't say anything about appropriate label, so I don't care about no stinking label. Let's quit this, clear this out, and go to math 9. That's for my integration from 1.866 to 3.519. I got to put my equation for VQ of t, which is 45 square root of x cosine. Make sure you are outside the radical. 0.063 x squared. Close that parenthesis out. Dummy variable. Let's see what it gives us. 106.109. I'll take it. 106.109. There we go. And we're done with 1C. Man, problem 2 was, this has been a breeze. This has been very pleasant. Let's see what 2D has in store for us. Let's not count our chickens before they hatch, as they say. At time t equals 0, particle Q is at position x equals -90. All right, that's going to be important. All right, that's Q, okay, at time 0, this is starting at -90. All right, using the result from part B, okay, and the function v of Q from part C, all right, approximate the distance between particles P and Q at time equals 2.8. So let's go to part B. Okay, part B, okay, this right here tells me the displacement from time 0 to time 2.8. And that happened to be 40.75. So particle P was at the origin. So that was at x equals 0 at time equals 0. So it's starting at 0, and it was 40.75 units to the right. Or in this case, do they have meters? Yeah, meters to the right. Okay, so particle P at time 2.8, okay, because 2.8 is right here, is at this position. Consider it on the x-axis, if you will. Okay, so let's go back here. So let's make a little note here. So particle P at time equals 2.8 is at 40.75. Okay, this is the thing we needed from part B. Okay, now it's saying use the function from part C. So we are going to use this bad boy right here. All right, so let's go back. Let's do this. We haven't done gray in a little bit. Let's go gray. So we need VQ of t, which is 45 times the square root of t times the cosine of 0.063 t squared. Now I need to find the displacement of that from time 0 to time 2.8. Again, integration. I don't want total distance. I want displacement because I want to know where it's at, not how far it's traveled. I don't care if it's gone to the right and it's come back to the left. I just want to know right where it is. So I integrate VQ of t dt from 0 to 2.8. Okay, but let's not forget, this didn't start at position 0. This was at position -90. This one, particle P, was at 0. So the displacement it moved to the right 40.75 meters from where it started. It happened to start at 0. This distance that particle Q is going to move is going to be moving from -90. So I got to start at -90. And then I got to add that movement to -90. It is not starting at 0. That's where the mistake can be made if you're not careful. So let me do this right now. I am going to be lazy. I'm going to copy this. Okay, I know I don't have a -90 there. That's fine. Let's figure out what this is first. Let's come all the way back here. My bounds are going to change from 2.8 is going to be my upper bound, and 0 is going to be my lower bound. Okay, and if we do this right, if we look near the battery, that yellow circle is still spinning. That means it's calculating. 135.937, that 7 will round up to an 8. Don't use this. We weren't at position 0, okay? If we're at position 0, that means it would have moved to the right, because it's positive, about 136 meters. But we were at -90. And we moved 135.93. So we got to add that to -90. So at 2.8 seconds, we're not at 135.9. We're at 45.938. 45.938. Okay? So now, particle Q at time equals 2.8 is at 45.938. We haven't answered the question yet. What is the distance between them? We got to subtract. So we take this answer and minus 40.75, and we get 5.188. We'll round that 7 up. So 5.188 is what we get. We take 45.938 and subtract 40.75. This is the distance between them. They don't ask us for labels. We are done. We killed it. 23 minutes. We did 4 sub-problems. We killed it, people. Enjoy 1 and 2 while we can. I'm sure the problems without the calculators won't be quite as easy. But we still got it because we're good at our algebra. I'll see you for problem 3.
Don't forget to subscribe and ring that bell.